Hi, everybody. So I have a new format here. I'm going to try to do this lecture on this whiteboard this time. And I'll be posting whatever comes up on my YouTube site. So maybe you could check it out there later. And I'll also, as usual, be posting a paper transcript of the lecture. Okay, so last time we were talking about the very important reaction of the carbonyl group with nucleophiles. So let's just do a rapid recap of last time. Recap of last time. Most important things that we said then was that the carbonyl carbon is an electrophile. It is attacked by nucleophiles. The carbonyl carbon is attacked by nucleophiles. The carbonyl carbon, this is an electrophile. That means it's electron poor. And a nucleophile is something that's electron rich. Okay, and we saw that the carbonyl carbon is an electrophile because of this, because the carbonyl oxygen is highly electronegative. It's greedy for the electrons of other atoms. It's sucking electrons away from the carbonyl carbon. And we express that withdrawal of electron density by the carbonyl oxygen using this formalism called resonance. See this arrow here? This is saying the oxygen is sucking electrons away from that carbon atom. And so we get a so-called resonance structure, which shows that that carbonyl oxygen has sucked so much electron density away from the carbonyl carbon that it has a negative charge on it. And the carbonyl carbon has had so much electron density removed from it that it has now acquired a positive charge. So this formalism here is the same as saying the carbonyl oxygen has a partial negative charge and the carbonyl carbon has a partial positive charge. And we use these lowercase Greek letter delta plus and delta minus to symbolize that partial positive and partial negative charge. So all I'm saying here is that the carbonyl carbon is electron poor. It's going to be attacked by stuff that is electron rich, and that electron rich thing is the nucleophile. Another thing that we talked about last time was that the nucleophiles attack along the Bürgi-Dunitz trajectory, so that nucleophile comes in from above and below the plane of the carbonyl, and it makes a 109-degree angle. And so that was summarized, or can summarize what we said last time with this drawing. We saw this quite a bit last time. There's the carbonyl group. It's planar, it's sitting on the tabletop, and the nucleophile, the electron-rich thing, let's put a negative charge on the nucleophile just to emphasize that it is electron-rich, comes in, attacks the carbonyl carbon from above or from below the plane of the carbonyl, making a 109-degree angle, as it enters. And furthermore, we said that the nucleophile follows the path of least steric resistance. If there's a big bulky group in the way, it's going to come in from the direction opposite that big bulky group, along the path of least steric hindrance. Okay, so, and we went through, at the last lecture, we went through several examples that illustrate this behavior. Okay, continuing our recap of last time, and this is going to lead into our lecture topic for today. And that was that there are trends in carbonyl reactivity. Not every carbonyl is equally reactive. Some are very reactive and some are very slow to react. So another thing that we mentioned at lecture last time is that big bulky groups at the carbonyl slow down the reaction with the nucleophile, which I'm just going to abbreviate as nuke, with the nucleophile. Okay, and we explained this because when the nucleophile comes in, we get compression of the carbonyl bond angle. So, for example, we said that if initially the carbonyl are here, initially this angle is 120 degrees, but when the nucleophile comes in, the angle is now compressed to 109 degrees because we're going from a steric number of 3 to a steric number of 4. And so now this angle is 109 degrees.